My short survey of the numerical techniques in galaxy evolution will be necessarily short because we lack the capacity of having hands-on part of this, which is essential. But certain things I will say and even reach some conclusions. Now, let me put it this way. As we talk, a revolution is occurring in astronomy. For millennia, it was an observational science, and then almost suddenly it became experimental science. So it became a mainstream physics. And I presume already now and definitely over the next decade, our colleagues in the physics department will not look upon us from above. Now, that really brings up additional responsibilities. But before I go to my responsibilities, where is Professor Calzetti? Yeah, you also, Professor Calzetti. I eliminated my comment about the dusty universe just as a proof that I can change to the best. But then I brought up this cartoon, which tells me, or tells you probably, that we don't know where this revolution will take us. As a revolution, it can be hijacked, and it can lead us to completely unpredictable conclusions. Think about this as at this point we can create virtual universes. Then if you just exaggerate this point, make it too extreme, in some near future we may be experimenting with real universes. Okay. So my first question, I will have a lot of questions to audience. Was the universe created analytically? There is this possibility because computers been invented in the 20th century only, and the answer is maybe, but not by us. And us as mortals, we need, if we want to answer these particular questions that you see here on the screen, we need something more than our analytical brains. And for example, if we want to describe and understand the orbits in evolving systems like planetary systems or globular clusters, we need to use techniques which are called few body codes. If we, and we really need a very special accuracy for this particular case to integrate the orbits. For stellar structure, understanding stellar structure and evolution, we need basically to solve the ordinary differential equations. We need to know some numerical algebra, and of course we need to know the hydrodynamics. Stellar and planetary formation. To hydro we need to add the MHD solvers, and probably also, again, the n-body methods. Galaxy formation in dark matter universe really requires or challenges these n-body methods to become very fast and brings up the advanced hydro. And then, as an astronomers, there is always the astronomical data analysis, image processing, and again, requires new methods like data mining, again, numerical algebra, and pattern recognition. So all this tells us that we are probably on the right track. Now, what I am going to talk in my short introduction to numerical methods or codes is now on the screen. I will say a few words about the N-body methods. I will talk about the gravity solvers. I will mention some ways to treat the hydro using the SPH, using the adaptive mesh refinement, or AMR, it is popularly known. And I will say a few words in the most interesting development in this respect, and that is the moving mesh methods. I will ask to talk also about the semi-analytical methods, but I will not do this. So, N-body techniques. And of course, I will limit the talk to Newtonian gravity, because otherwise we will never get out of this black hole. The first usage of N-body technique was in 1941 by Holmberg, and he used this beautiful analogy between the point sources of light as given by electrical bulbs, and studied interaction of two disk galaxies. He even got results, but I will discuss this in the section of actual astronomy and not numerical methods. The direct N-body simulations been first implemented by von Horner in Heidelberg. Maybe you know this name, being the father of the doomsday of our civilization, who for the first time compiled a list of five issues why we all are doomed, like genetic degeneration, self-destruction, and others. Okay, but that's for a different conference. Then Sverre Arset really made the application of direct N-body simulations as his life hobby. Okay, actually, what he wanted to do and largely succeeded. You know that Newtonian gravity has this singularity at small radii, yes, when you have 1 over r, and he wanted to eliminate this from numerical simulations, from calculations actually, and this method is today known as orbit regularization. Actually, he succeeded very well about this. Well, there are other applications of these N-body techniques. I originally wanted to talk about this solar system visualizer, but then left it just as a website. And now, what I wanted to show you, this synthetic science or synthetic art, which was produced by John Dubinsky, just based on N-body. Maybe light can be taken down a little bit. After all, this is astronomy. So this, what you see here, is a pure collisionless dynamics of galaxy cluster formation. And people like to see it and at the same time to listen to serious music. Well, to go to the real stuff, we all know the application of N-body technique to two-body system. It's just a Kepler problem. You get this beautiful pair going around the elliptical orbits around the center of mass. And there is a clear analytical solution for this that we give to our students. N equals 3 already doesn't have an analytical solution. However, it has some approximations to the analytical solution. And then what we are really interested, at least here at this conference, is where N is large. Not too large, but large. If we try to simulate galaxies, we simulate the density field using the massive particles. We use the Newtonian, does it work? Well, how long do I need to wait? I have only 1 hour to do. Yeah. Okay. Okay, so it's gone. So we have different methods, and I will not talk to all of them, just highlight. We have the direct summation that I will mention, particle mesh approach, which I also will mention, particle mesh, which I will not mention here, tree chords, and then, of course, at the bottom you see that when we take n to infinity, then to the limit we have a continuous approximation, and I should talk about this as well. Now, the direct summation codes, or as they are called, PP codes. I mean, basically, the only thing they do is they evaluate the forces and then integrate the orbits of particles. There is, in this approach, there is no approximation. The solution is exact. It is of highest accuracy, and close encounters in this approach, close encounters and bound systems are treated exactly. Well, basically what they do in this approach, they calculate forces on all particles to eliminate the singularity at the center. Softening parameter epsilon is used. The only problem is would be if we use in this approach the softening parameter, it basically eliminates the most interesting case in, for example, dynamics of globular clusters. That's hard binaries and so on. So either we eliminate the softening parameter completely, or it should be as small as possible. In this direct summation, basically, all forces are calculated in the most straightforward way, and so the number of operations is n times n minus 1 over 2, which is basically n squared. And the limit is 10 to the 4 particles. However, with a very special purpose hardware, which is called GRAPE, this limit can be superseded, maybe up to 10 to the 7 particles, and the latest GRAPE 6 system now is made as a supercomputer, both in Heidelberg and in US, but it is used for very well-defined purposes only. Now, do we really need to calculate forces on every particle or between every two particles? No, I mean, luckily for us, the distance between galaxies is still at least 10 times larger than the sizes of galaxies, which means that we really are not obliged to count all the pairs. And that is the essence of the Barnes and Hart algorithm, where you have a hierarchy. Some particles interact directly, and some particles interact indirectly through some averaging. That can be done in the plane, but it can also be done in the 3D space. Then you get this oak tree, and instead of having smaller number of neighbors, you have 8 neighbors. So what really is done in this approach is that all the space is subdivided into volumes of particular shape, say cubes, and then to the point that each cube consists only of one particle, and then the particles that are close to each other, the interactions are calculated directly, and those that are not too close, and the angle at which you see this particle from some other particle is smaller than some prescribed angle, then you just average these particles in the larger cells. In this particular approach, the number of operation is not n squared but n log n, and that substantially improves the performance. Now, Unfortunately, the 3 codes are very good, but up to some number of particles, like 10 to the 7, 10 to the 8 particles, which were not really, were not yet freely operating with this amount, but some of us are, and then about 1 billion particles or so, we need to use a different approach. Instead of calculating forces directly, we calculate the potential. And then using the potential gradient and the Poisson equation, we can calculate the forces. So in this respect, what do? We first assign particle to a particular mesh, compute the mass density. We solve the Poisson equation with boundary equations. We compute forces on particles, and we integrate the motion of this particle. So here is one-dimensional example. We discretize this one-dimensional space into ng zones. There are particles within each zone, so we can use just the most primitive way, calculate the mass of the particles in particular zone, and get some results. So this is how to calculate rho. The next step, we solve the Poisson equation. Again, in 1D, of course, it's an elliptical PDE. We calculate the densities and the potentials in the grid centers. We calculate the forces in the step number 3. We calculate we implement, of course, the boundary conditions. We should not forget. We implement the boundary conditions, and then we calculate the. In step 3, we calculate the forces acting on the particles along the recipe that I already mentioned. Instead of calculating the forces directly, we already calculate the potential. Then we calculate the forces at the boundaries of the cells, and then calculate the orbits. Now, unfortunately, if we have a fixed grid, it is not always suitable for solving a particular problem. For example, if the problem has hierarchy of resolutions, then how do we approach this problem? We need either to, from the start, to have a grid which is very detailed, and that is next to impossible, and it's also waste of taxpayers' money. But what we can instead, as the system evolves, and there is a need in particular region to resolve it, we can bring up recursively a grid and a fine grid in this place. And this way we can have increased the dynamic range, and usually, depending on the number of levels of resolution, we have the dynamic range, which is 2 to the power of n levels. So this is called the adaptive mesh refinement, or AMR, where at the base you have a very coarse grid, and you dynamically bring up additional resolution. You flag first, make a survey of the space. You flag places where you need additional levels of resolution, and then bring it up, and the resulting grid structure is dynamic or adaptive, which is very important. Okay, when we increase the number n, the number of particles, even more importantly, when we deal either with phase space, which means configuration space 3D, and the velocity space 3D, we need to solve Boltzmann equation. This is very expensive, and it's actually 6 plus 1 dimensions, okay? And even with the modern computers, you cannot go far. But if you can use the hydrodynamical approach, using the three hydrodynamical equations, the mass conservation, the momentum conservation, and energy conservation, then there is some hope. And the interesting, I would say, revolutionary method that was invented sometime in the mid-70s, as they say, originally it was Leon Lucy's idea. The particles, it's essentially n-body code. But the particles, the gas particles, are averaged over some region using what is called the smoothing kernel. And I would like to show you all what I mean by this, but no, it doesn't. So you see it on the right. Approximately about 100 particles are needed in order to average such properties, a density of the particles to take the discrete n-body code and convert it into, take it in the limit of hydrodynamical limit. So you have density, you can define the momentum or Euler equation, and the beautiful thing about these codes is that you can take them together naturally with the n-body code. And so we know that we have stars in addition to to the gas, we have dark matter, and who knows, maybe we'll have something else. So they come together in a very nice package. There are, however, some problems with SPH, and I must tell, it is not a criticism. I think we don't yet know what SPH is capable. But there are certain things which border on the limit of our knowledge of physics. We still have no treatment of viscosity in classical physics, so we don't expect that SPH will solve this problem naturally. So one brings up, maybe this, yeah. Yeah, but where to plug it? Okay. You need to switch. Okay, so okay, so yeah, it's working, but too well. No, it will go, of course, not where I want. Okay, so what we have is the description of shear, and especially description of vorticity and viscosity, which have empirical coefficients, which we can guess only what is their value, and that is definitely a limitation of the scheme. As an example, I have a case of vorticity behind the foil. Behind the foil, you see the problem here is, for some reason, and it could be related to this viscosity coefficient alpha, is that the vorticity dies out behind the foil too fast. So it's not a good description of what's happening in reality. So what is the strength of SPH? It's Lagrangian scheme. It has particles sitting where we want them to be seated. Okay, that's where the resolution is, where the matter is focused. It's easy to interface, I already mentioned, with n-body codes, and especially with the three codes. It's easy to code, and it always runs, as people tell me, even when they produce nonsense, and this nonsense is sometimes published. So weakness. Well, again, it was a strength, it's a weakness. Lagrangian code, it gives a poor resolution in the places where material escapes, and you want sometimes to see what's happening there. Okay? So, as I mentioned, it's a weakness that it always runs with misleading, sometimes, of course, with misleading results. It is slow because, as I already mentioned, about 100 particles are needed for, to put in the kernel to smooth, to have this hydro approximation. And it has this artificial viscosity, which I mentioned in the previous slides, so it is somewhat diffusive. And there are also open questions which we don't understand about SPH. It may suppress some of the hydrodynamical instabilities, as we recently learned, like Kelvin-Helmholtz instability, turbulence, and this is not good, of course. But as I said, this is the SPH that we have today is not the last SPH that we will probably have. So, alternative approach to SPH are grid-based Eulerian codes. In this case, you solve directly the Euler equation, and this is a great advantage. So, as I put it here, that Eulerian equation is solved directly. And the weakness is, of course, that it has only a limited resolution. So, you need to go to AMR techniques, to adaptive mesh refinement, and that may help, but not completely. Then there are open questions about Eulerian codes that we simply don't have yet answers. There are suspicions that they are not Galilean invariant, which is not so good. They have numerical viscosity as well, and so the mixing of different layers of fluid are not really well controlled. So what do you do when you have all these codes which can bring you funding, publications, but you are not sure how to deal with the results? Well, you test them. And there are a number of standard tests. And the most beautiful tests are, of course, those that when you compare the numerical solution with the analytical one. So I mentioned few here. Polytropic sphere, like just a density profile in polytropic sphere or pulsations of polytrope. The shock tube, the accretion, position of accretion shock, the two fluid instabilities, and more, okay? But the number of analytical approaches is very limited. So what do you do if you don't have analytical solution for comparison? You use what Frank et al. Used in Santa Barbara cluster comparison when they compared 12 codes. And there are names. What you see here, there's a formation of a cluster of galaxies. On the left, pure dark matter. On the right, the gas component. And these are both mixture of Eulerian and SPH codes. And so the result is not bad. You see that more or less the same structure forms, although there are embarrassing details which are missing in some cases. So agreement within factor of 2, I saw worse cases. Now, how I want to finish my short introduction of these numerical methods is by talking about the new approach, and that is not only adaptive mesh, but moving mesh using tessellations. This code is called AREPO. It is not yet available to everybody, but there are some results which are already available. Now, what are the tessellations? Well, tessellations is something that most of us, those that go shopping, at least 50% of people here, I'm sure, like shopping. So what it really is doing is, well, tessellation, which is definitely a Greek word, means basically decomposition. When you try to decompose the space based on distances and a number of specific objects, a family of objects in space. So you call these objects that you decide what they are. You call them seeds. And these seeds will be associated with cells. Now, what are the cells? The cells, which you see here in different color, each cell is a set of points in space whose distance to the object, which are the central points here, smaller or equal than their distance to other objects. And as I said, shopping is something that almost all of us like to do, and then we intuitively solve this problem by going to the closest supermarket or whatever is your preferable place of wasting money. Okay, so what about this moving mesh using tessellations? What Walker-Sprengel succeeded where some other people failed over the years is by creating these points around which he is moving, is putting a dynamic mesh. When these points are stationary, when the mesh is stationary, then we just have a regular Eulerian approach. But if not, if they move, we have Lagrangian dynamics, so it takes the best out of the SPH and the AMR codes. So it's adjustable resolution, which is done automatically and continuously, and has very high accuracy. Now, here is a simulation of mergers using this approach. Looks normal, right? But sometimes to be convinced that this method is interesting, one should like to see how all this moves. Okay, so before we go to this, here is an example. You have the AREPO, the new code, on the left. You have here a layer, two fluids, which are interacting because there is a relative velocity of these layers with respect to each other, and the instability, the Kelvin-Helmholtz instability develops on the boundary, quickly goes into nonlinear stage and goes and produces vorticity. So Athena, which is a Eulerian code, is on the right, and AREPO is on the left, and there is no obvious differences between two approaches. But let's see how it works. And I'm giving you the example of Kelvin-Helmholtz instability. So initially you have plane parallel layers, and you see that Kelvin-Helmholtz instability quickly develops, and you see also how the tessellation problem is solved, and how the mixing occurs, and then the instability proceeds, but on different level. Okay, this is very impressive. It is even more impressive if I would show you this with the same example with SPH, where you would see no evolution whatsoever. Okay, another example. A point explosion in infinite atmosphere, known as Sedov-Taylor solution. And you already smell what to expect. I mean, there is a strong shock that forms here, and shocks are always problematic in any hydro. You usually spend shocks and boundary conditions, that's where you spend 90% of the time. Okay, I mean, the boundary conditions here are simply reflective, so the rest of the evolution is not interesting. And then the last one is the differentially rotating disk. Although I know which way it will rotate, but there is this feeling that initially it starts a little bit in the different direction and then proceeds the right way. Anyway, this is very impressive because this is one of the ultimate tests for any hydro code. Okay, so if I would like to conclude this part, how do I see the future here, the future of this quiet revolution? Well, what we need is, of course, the increase in the performance of hardware. We need new hardware. We need computing power. This is not new. We need new, reliable algorithms, like the tessellations that came after many years of failure. We need, I mean, you know what I mean, of course, that we need a really advance in subgrid physics. We need codes that are in public domain, and these codes must be unified, and not each one is doing whatever, and then nobody compares the results, only after published in UpJ or some other journal. We need the Santa Barbara type code testing, and no result over interpretation. Unification and visualization. Visualization must be unified, and not every time you start to work on this from the scratch. And then I added 2 lines of my personal conviction. We need undergraduate and graduate level student computer literacy, not only reading emails and playing games. And I'm talking about physics students. And then I strongly demand bringing back hydro to the class. Today, nobody is teaching hydro anymore in the universities. Only some obscure astronomers. And what do they know about this? Okay, that brings us to the real stuff. But all these numerical methods, in all 4 my talks, will be, they will be always around. So I will talk now about the galactic disks and their evolution. I probably will not get far away today. I will ask many questions without anticipating any answers, but maybe somewhere it will resonate. Well, talk about galaxies. We know only 3 types of galaxies. The ones that have disks, the ones that don't have disks, which we call ellipticals, and the one that we don't know how to classify, so irregulars or peculiars or whatever. Okay? So with these 3 types of galaxies, the goal of explaining them, how they originate, doesn't look hopeless, right? So here is a beautiful paper that was published about a year ago by Delgado Serrano et al., where they took the local galaxies at redshift 0 and constructed kind of a Hubble fork, and then took galaxies which are, I mean, from the times which are like 6 gigayears in the past, and constructed or attempted to construct the same sequence. So what do we get? I mean, not many changes, but the changes that are noticeable here are really challenging. Now, the number of ellipticals didn't change really a lot, and there's zeros as well. But the number of spirals from redshift 0 to redshift 0.6, of course, went down by a factor of 2. And the fraction of peculiars went up by factor of 5. So I would call this evolution, with your permission, and that simply means that if you agree, then we are all get employed for the next generation at least. So here is another similar diagram that is actually 10 years old, where Brinkman and Ellis calculated the redshift evolution of merger rate up to redshift 1 approximately, and that of the mass density of peculiars. And I'm not even stressing the similar or somewhat similar evolution between the... I only want to stress the increase in the density of peculiars in the early universe. Okay, so this will be taken as evolution. Well, if we agree that this evolution, then of course the only thing which remains to explain is what are the reasons for this evolution. Well, you immediately, or basically what you need to explain, how the Hubble sequence originates. Why does it look the way it looks today around us? So 2 extreme views. And you know, extremist views are usually wrong, so they must be blended. And that may be our work. So one possibility that all what we call the galaxy evolution is really subject to initial conditions. If we know the initial conditions, and we know them pretty well, then the rest, there's no chance anymore, no place for a chance. So nature decides, nature performs, and we get the result. So, you know, when you go to the high redshift universe, when you go to a universe which is above redshift 6, which was never mentioned here at this conference yet, say between redshift 6 and 10, then the universe doesn't look isotropic and homogeneous in the galaxy universe. Yes, if you average very well, it will. But what is the point to average over the spread these few galaxies that are there at redshift 10? They concentrate in few particular places, which are the overdensities. Galaxies form there, and we basically can ignore the field galaxies at this redshift. Okay? So, what is the alternative to this? The alternative is that it's all due to environment, and initial conditions don't matter at all. Everything is the result of galaxy interactions and other types of interactions, like, for example, IgM galaxy, ISM galaxy interactions, and the list can be actually long. So it's nature versus nurture. And maybe the actual solution is somewhere in the middle. Well, to be seen. What are the issues with structure formation in the universe? I mean, these are, you know, we're kind of accustomed that the grand design structure formation in the universe on the larger scales is basically solved during the last generation, right? But nevertheless, some caveats still exist. Well, there are two alternatives, of course, which have been resolved. This is the structure formation of top-bottom versus bottom-up. Okay, so you pick up your favorite one. As I said, we more or less understand the structure formation on larger scales. But what is the role, or if at all, of baryons at this time? They are the minority. Do they matter at all at these early times? And if they matter, where are the baryons that matter? In fact, we even today miss half of the baryons, right? So doesn't look good. Then, if the baryons, according to the classical, the paradigm, baryons follow the dark matter. At some point, they decouple, because the dark matter doesn't follow exactly the luminous galaxies. Okay? Then where do they, at what point do they decouple? Customary to assume that they decouple when the baryons fall into virialized halos. But this is not what we observe in numerical simulations. It could be that they decouple already in the filaments, and I just don't have time. So, you know, filaments form before the intersections of the filaments form where the clusters of galaxies form. So it looks like the thing happened earlier, but we don't understand it yet fully. Then, when the baryons collapse and assemble in dark matter halo, we get the mass and the angular momentum distribution. So based on this mass and angular momentum distribution, that should tell us everything about the galaxies. Where do galaxies form? When do stars form, of course, in the galaxies? And this is not such a trivial question. I mean, normally we say, oh, well, this part which of the halo that forms stars, this is what we call the galaxy. But if I will have time, one of the other talks, I will show you that this is not a good definition. I mean, it's not a clean definition. I don't know if there is a clean definition of what is a galaxy. Now, When the baryons fall into the dark matter, they fragment and they form objects, say they form stars. So in this process, is the fragmentation encouraged or it is suppressed? It would be nice to understand processes that act in each direction. And then the question, when the baryons collapse in dark matter halos and galaxies form, is the angular momentum of baryons conserved? More questions. And, I leave the large-scale structure. I go to subgalactic scales, galaxy formation, not dark matter formation. A simple question. Why do disk forms? And a related question. First galaxies, will they be disks or will they be ellipticals? Is the role of feedback, the feedback plays any role in deciding which type of galaxies we get? And then, well, there are different feedbacks. I mentioned supernova or supermassive black hole feedback, but the list is long. Archaeology. Well, some people claim that if we just understand how the galaxies moved and looked at higher redshift, that will help us to understand why they look the same way, particular way today. And the related questions are, whether you like mergers or you don't like mergers. I don't know what is the weight of mergers in galaxy evolution. I'm completely open. I ask the simple question, can the disk survive major merger epoch? Okay. Then thick disks, which have been mentioned already in this conference. But the $100 question, are the thick disks coming from mergers, or they are just result of supernova puffing up the thin disk galaxies? Then how much streamers in the thick disk and in the halo can tell us about the galaxy formation process? Galaxies sit in halos, at least most of them. They must interact, especially because the halos, at least at high redshifts, are universally triaxial. There's no question about this, whatever you think about numerical simulations. Halos form with a particular distribution of triaxiality, and they are very triaxial. Now, the disk galaxies, and I'm not even talking about ellipticals, but the disk galaxies can be non-axisymmetric as well, because a large fraction of these galaxies are barred at all the redshifts that we see so far and can determine their morphology. And so this relates us directly to what is the dynamic of disks at different redshifts. How do they exactly interact with triaxial halo? And is it actually possible that at some point, if the halo is too triaxial, the disk cannot even form in such a halo? And then comes the heart of the secular evolution, the stellar bars. Whatever we say about stellar bars, we have no idea how they form. Yes, as Leah said, there is a theory, but for every theory there is another counter-theory. And every theory has some positive aspects, some negative aspects, but we don't know yet what is what. So we don't know whether the bars form internally as a result of internal evolution or externally driven evolution. Okay. Gas. Gas is a small fraction of matter in the universe. I'm not even talking about total energy in the universe. And so we all know that the gas helps to form the spiral structure. But is this the main aspect of the gas? We know also the gas helps to form star formation. But what happens beyond these two obvious cases? What is the dynamical effect of the small fraction of gas on the large fraction of dark matter. And here comes this interesting question that we will need to answer at some point. Is there any correlation, a very simple question, is there any correlation with the mass fraction of baryons, gas, and stars with the mass of dark matter halo? Disk morphology, a lot of discussions here, and I just mentioned here because I was asked not to talk about this, so I will not talk about this, but somebody will need. Then the $100 question that causing me sleepless nights. Are we doomed? I mean, in the sense that are disk galaxies doomed? Oh, why? And so, are these galaxies doomed? In the sense that ultimately, evolution is that there are these high-density regions, and the galaxies that are at disadvantage in forming in low-density regions, they fall to the center. And you remember just the previous speaker talk about the density morphology relationship. Is this relationship obvious at high redshift? I will clearly show you that there are some questions about this. Then comparing, of course, a very important issue, comparing the simulated with the observed disk, and asking this important question, after all, what regulates the star formation in the disk? Is it the stellar mass loss, or this is the infall, whatever it is? Large merger, massive mergers, or minor merger, or simply cold gas accretion, it is important. And, of course, the Milky Way, is a test lab. Everybody understands it. But I am quite pessimistic about this, that it will help. Because I remember that Crab Nebula, that everybody calls a test lab for the pulsar for supernova remnant evolution. But we don't understand it much less than others. The center of the Milky Way is kind of a proto-AGN. We don't understand what's going on there. And many other things. So maybe we know too much. And I have no time to tell you this interesting jokes about the three cowboys, which is very much related to this. Okay, so our goal is, of course, to understand or to build a realistic disk which is compatible what we actually see. And that means we need to understand how the galaxies form and quantify these aspects and compare them with observed galaxies. But because we don't know how to isolate galaxies, their formation and their evolution, then the question is, of course, can it be isolated? We need to spice and to mix it with the rest of the universe, hopefully not with too much of this universe, otherwise it will be too salty. Now, there is this dichotomy of top-down and bottom-up scenarios. So if I can be kind of obnoxious and just say that on the left, the top-down scenario, you win a lottery ticket, you become a millionaire. You share it with your immediate relatives. They share it with their relatives. And then at the end, you have a bunch of poor relatives, but many of them running around. As an alternative, you go on the street and you find a buck. You take it to the nearest bank, and then you go again, and you find another buck. And that for the rest of your life, sometimes it's portions of the buck. So you become a millionaire at the end, right? So that's basically these two scenarios. And the original idea, if you are aware, was that paper of Egan, Lindenbell, and Sandage, which all smiling here from these pictures, but they basically been in favor of the top-down approach, and they said, well, if you would take isolated cloud of gas and let it collapse under its own gravity and form stars, that can very much explain details of what happens in the Milky Way. Like the first stars will be metal pools, they will be on highly elongated, almost radial orbits, and then the guys that form later will be metal-rich and form a disk. Okay? So that is this approach, but we know today that this dichotomy resolved in favor of bottom-up path. And there is a strong evidence that galaxies, for example, formed before the clusters of galaxies formed. And there are many clusters of galaxies that are still forming today. This is the epoch of galaxy cluster formation. So the way we understand today that the growth proceeds hierarchically, okay, and the smaller structures form and merge and form progressively higher, more massive objects. What are the issues, in one few sentences, with the monolithic approach of Egan et al.? Well, I mean, the list is really long, but I picked up randomly some. The problem is, for example, with the globular clusters on retrograde orbits, which they would have difficulty to explain. The age spread of the globular clusters, which is at least order of magnitude above the few times 10 to the 8, which is just the dynamical collapse time. And then the issue with the metallicity, abundance in the globular clusters, where you actually have the metal rich, but the guys that are in the halo have quite a range of metallicities, contrary to the idea. So, in fact, many of the above problems that are mentioned here and not mentioned can be solved if the solution is not a monolithic approach, not from top down, but from the bottom up. How much time I have? I started 10:20. Okay, so, okay. Many years ago, this strange person on the right measured dispersion velocities of just 8 gases in coma and got a fascinating number, 1,000 kilometers per second. So using then available value of, the available value of Hubble constant, 500 kilometers per second per megaparsec, he actually estimated that there is the mass density of coma is 400 times more than the luminous matter in coma. And then at present the discrepancy is only 50, but it's still impressive. And then he asked his famous phrase that something is missing in this universe. He had other ideas as well. He coined the word supernova. He also coined the word, well, that's with Baade, and then he coined also the word, the understanding of predicted gravitational lenses. Then, in 1984, based on numerical simulations, one of the highlights, achievements of N-body simulations, Simon White said that neutrino ruled out neutrino-dominated universe as incompatible with observations, again, based on the N-body simulations. Approximately at that time, Dick Bond coined the name cold dark matter, and then, although some people dispute it, Simon White in 1987 said that basically that Zwick's missing matter is this cold dark matter that we are discussing now. So that is the kind of a background of what I am going to discuss for the next 3 talks, and that actually symbolizes the end of the dark ages in the universe And that's when the first stars, the population 3 stars may be formed, but I'm not going to discuss them. What are the challenges in understanding the process of galaxy formation? Challenges are numerous. Nonlinear dynamics. We don't understand star formation. We don't understand feedbacks. We have no description of real understanding of turbulence. And of course, observers work not hard enough, so we don't have insufficient number of observational constraints. And there are, of course, technical difficulties. Some I discussed in the first part of my talk. But the main technical difficulty is, of course, the large dynamic range, which is very difficult to swallow, not only to swallow, but also to digest. Now, we operating at some point today under a particular paradigm which was coined about, 25 years ago by a number of people like Reason Why, Fallen of Stature, and then summarized again in this Momau and White paper, and some earlier works that, I'm not talking about history here. Now, what is in essence this paradigm? This paradigm is basically a two-stage theory of galaxy formation and clustering. You have dark matter halos forming in potential wells, gas cools and form stars within these wells, and prior to the gravitational collapse, the halos acquire angular momentum, probably during the linear stage before the maximum expansion of particular halos. So they interact, they acquire angular momentum, and I would want to introduce now the angular momentum per unit mass, the little j, as opposite to large j, which depends on mass. So baryons follow, in this paradigm, follow the dark matter in the initial stages of the collapses, and j apparently was assumed as being conserved, and not only the value of j was assumed to be conserved, but also the distribution of j, or m as a function of j, the mass as a function of j, or j as a function of mass, whatever you prefer. Then the baryons continue the collapse, and all this happens with constant j. I will take another 2-3 minutes, and then I will stop. So we have this conjecture. The observable properties of galaxies depend exclusively on the mass of the halos, of the host halos, and their specific angular momentum, and the distribution, of course, of this specific angular momentum. So this, as I said, this is conjecture. And this is the paradigm that we're operating with it. So if you have low specific angular momentum, then you have accretion onto the central region of a galaxy. That dark circle symbolizes the halo. You have star formation. You have central starburst. And you form the galactic bulge. And maybe you form also the supermassive black holes. When you have higher j, the question is also higher, how much higher, you form a galactic disk. And you have the advantage of self-regulating star formation within the disk. It is the j, the specific angular momentum, which decides what is the disk size, what it is its surface density, and what is the star formation timescale. Then come the caveats that slowly started to pile up in addition to the paradigm, and ultimately they will result in the paradigm shift. It was found out by numerical simulations that the dark matter density profile in the halos is a two-parameter family, so-called NFW profile, which leads to universal rotation curve in the galaxy. So the density is color-coded, the NFW density distribution, and it results in this flat rotation curve. So the new thing was also understanding at some point, and that is not a final word here, that baryons can, as they concentrate in the center, they can drag dark matter with it, so that's kind of an adiabatic contraction. The $100 question. Is this universal process? Or maybe if baryons don't come in smooth way, but rather clumpy, maybe there may be caveats in this adiabatic contraction problem. Now, it was also understood that bulges can form from low angular momentum baryons, and that supernova feedback can do some changes. I probably will stop here and take questions if there are.
This is a school, and we're very interested in, and I always very much like, as a comment, individual papers that present new results that ought to become tomorrow's intuition. Now, I just want to mention one paper which sort of fits in very early in your talk in the sequence of discussion of techniques, which I'd really like you folks to know about. And I'll spell the first author's name. It's S-Z-E-B-E-H-E-L-Y. S-Z-E-B-E-H-E-L-Y.
What was the beginning?
Zebehay. It's a Hungarian dude. And his co-author is Peters, which is spelled the way it sounds. This is about the early 1970s. And they made a very elegant calculation of a three-body problem, masses 3, 4, and 5 on the corners of a 5, 4, 3 triangles released at rest. Very specialized problem. Very elegant result. Energy equiposition happens. The heavy guys sink to the middle, capture each other into a binary, and fling the light guy out really fast. And the reason I like this is because of the way it captures intuition of the sort that I've just described. And it's a very nice model of what we can expect will happen in the centers of galaxies when mergers produce triples of supermassive black holes. It's also very relevant to cluster evolution. But I just wanted you to know about this paper because it really distills intuition in a very nice way.
Are you going to discuss also the dark matter distribution? I mean, with respect to the light? Because one of my issues, things I'm worried about, is that some objects, especially dwarf galaxies, some dwarf galaxies seem to have enormous M over L values, and this is because simulations show that the halos are very massive and the galaxies that one observes are very small. And it might be right, but it's counterintuitive. I mean, I like to go to some universe where you see where what you see is what you get.
Well, to answer your question this is a very important question, and I mentioned in one of my questions whether the luminous matter, whether the mass of the halo and the angular momentum of the halos, whether they correlate tightly with the masses of luminous matter, dark matter with luminous matter. I don't know if I will have time to go into this, but I assure you that this issue will pop up periodically, at least in my talks.
You said well, a few minutes ago, that galaxies, mass and the halo and angular momentum sort of dictate whether we have a bulge somehow or where a galaxy a disk. So there is like a destinity. We have a certain mass, a certain angular momentum, and we have one of the two scenarios. Is that what we should understand? And of course, there is no possibility of any evolution of these two of elliptical of bulge on this prescription is not possible in principle. So we have already decided at the beginning, depending on the mass and the J, what is going to be a bulge, what is going to be a...
That's the paradigm, that's the idea of the galaxy formation theory, if we can call it theory, that was proposed in the late 70s and the beginning of 80s. And that is something that was tested over the next 20 years. There are successes in this direction, but new things that have been discovered, and that's the beauty that we not only test the old stuff, but we sometimes discover new stuff, they will lead, and they're already leading to the paradigm shift.
One more question from the older crowd.
Yes, Professor Calzetti.
The model on the right is actually very thought-provoking because, it's the current thinking of a lot of people doing observations and trying to model them, that you form a sort of proto-galaxy, maybe a disk at redshift 3 or 2, but then there's a lot of subsequent accretion of gas to continue the star formation, and I'll show a model for that tomorrow. So one wonders, though, you have a given specific angular momentum at the early stage from forming the sort of initial protogalactic clump, but then the later accretion may have a very different specific angular momentum. And so it seems a little, I'm not saying that's wrong, but it's a little puzzling that you don't see more evolution of the angular momentum in galaxies, or maybe one does, maybe it's just not measured.
I think
but
you're right.
It seems like intuitively there should be major changes in the sort of spin of galaxies as a function of time. Sort of from redshift 2 down to 1 or 0.5.
Well, yeah, a related question is whether the disks that we see today, when did they form? Just by looking on the stellar populations in the disk will not answer this question. Yes, the stars may be very old, but the disk may be dynamically young. It cannot be vice versa. So, well, this is very important question.
The point is not only do you supply fresh gas, but also may have an angular momentum very different.
Well, the question whether in the process of this evolution, when you get influx of matter with different angular momentum, does it eliminating the old disk, which would be very interesting. There was, for a few years, there was a particular vision that answer is that this influx always leads to destruction of the disk, if it is violent. If not, if the disk just sits quietly and gets this like high velocity clouds, then, but that's kind of boring. But if there are mergers, then it was a perception that the disk will not survive. This is not anymore the perception, as I will talk.
No more questions? Come on, you're very quiet in asking questions. It's a school, you can ask. Anyway, let's thank Isaac again for his lecture. I've got a couple of announcements before coffee, because we're running slightly ahead of schedule. I hope the coffee's ready. I think it is. First is that there's a copy of the new timetable at the entrance to this room. You can take